Welcome! In this session, we'll dive into LeetCode problem number 1192, critical connections in a network. This problem is a fascinating graph-based challenge that involves identifying critical connections in a network of servers. We'll explore the problem details, examine the solution approaches, and discuss the concepts needed to solve it effectively. Let's get started. In this problem, you are tasked with analyzing a network of servers. The network consists of n servers, labeled from 0 to n1, connected by a set of bidirectional links called connections. Each connection is represented as a pair, A, B, indicating that server A can directly communicate with server B. The key challenge is to identify the critical connections in this network. A critical connection is one that, if removed, would result in the network being split into disconnected parts. Your goal is to return all such critical connections in any order. The input will include the number of servers, n, and a list of connections. The output should be a list of these critical connections, where each connection is represented as a pair, U, V. This helps us understand how the network structure depends on certain connections to remain fully connected. Let's consider an example to make the problem clearer. Suppose n is 4, meaning there are 4 servers labeled 0 through 3. The connections are given as 0, 1, 1, 2, 2, 0, 1, 3. Visually, this network can be drawn as a graph where server 0 connects to 1, server 1 connects to both 2 and 3, and server 2 connects back to 0, forming a cycle. In this setup, the connection 1, 3 is critical because removing it would split the network into 2 separate parts. Specifically, servers 0, 1, and 2 would form one connected component, while server 3 would be isolated. To analyze this further, removing the connection 1, 3 results in 2 disconnected components. The first component consists of servers 0, 1, 2, which remain connected through the remaining links. The second component is simply server 3, which is no longer connected to any other server. This makes 1, 3 a critical connection. On the other hand, no other connection in this network is critical. For example, removing 0, 1, 1, 2, or 2, 0 would still leave the rest of the network connected. Now, let's look at another example. If n is 2 and the connections are 0, 1, the network consists of just 2 servers connected by a single link. Removing this link would disconnect the network entirely, making 0, 1 the only critical connection. For a third example, imagine n is 5 and the connections are 0, 1, 0, 2, 0, 3, 0, 4. This network forms a star graph, with server 0 at the center connected to the other servers. Here, every connection, 0, x, where x is 1, 2, 3, or 4, is critical. Removing any one of these links would isolate the corresponding server from the rest of the network. For instance, removing 0, 1 would disconnect server 1, and the same applies to the other servers. This example highlights how certain graph structures, like a star graph, can have multiple critical connections. Finally, let's consider some edge cases to better understand the constraints and behavior of the problem. In a small network with just 2 servers, such as n equals 2 and connections equals 0, 1, the single connection is always critical. In a fully connected network, where every server is directly connected to every other server, there are no critical connections because removing any one link still leaves other paths available. For a star graph, like the one we just discussed, all connections from the central server are critical. Additionally, for large networks with the maximum constraints, the algorithm must handle up to 100,000 servers and connections efficiently. These examples and edge cases illustrate the variety of scenarios this problem can encompass, from simple to highly complex networks. To solve the problem of finding critical connections in a network, we need to identify edges whose removal would disconnect the graph. These are known as bridges in graph theory. One of the approaches we could consider is the brute force method. The idea here is to remove each connection, one at a time, and then check if the network becomes disconnected by performing a graph traversal, such as depth-first search or breadth-first search, from any node. While this approach is simple and intuitive, it is computationally expensive. For each edge, we would need to traverse the entire graph, leading to a time complexity of O, m*, n plus m, where n is the number of nodes and m is the number of edges. This makes the brute force approach impractical for large networks, especially when n and m are in the range of tens or hundreds of thousands. As a result, we need a more efficient solution for larger datasets. A more optimized and widely used approach is Tarjan's algorithm, which is based on depth-first search and leverages concepts like discovery times and low link values. The key idea is to identify bridges, which are edges that do not belong to any cycle in the graph. During the DFS, each node is assigned a discovery time, representing when it was first visited, and a low link value, which represents the smallest discovery time reachable from that node. If the low link value of a neighboring node is greater than the discovery time of the current node, the edge connecting them is a critical connection. This algorithm is highly efficient, with a time complexity of O(n plus m), making it suitable for both sparse and dense graphs. Compared to brute force, it avoids redundant traversals and scales well for large networks. Another approach is using union find with backtracking. This involves tracking connected components during DFS and checking if removing an edge splits a component. While it's a valid alternative, it tends to be less intuitive than Tarjan's algorithm and may require additional complexity in implementation, which is why it is less commonly used for this type of problem. For this problem, we chose to implement Tarjan's algorithm due to its efficiency and clear applicability to finding critical connections. The insight here is that critical connections correspond to bridges in the graph. By using DFS in combination with discovery times and low link values, we can identify these bridges in a single traversal. This makes the algorithm both efficient and elegant. When comparing strategies, the brute force method, while simpler to understand, is computationally prohibitive for large graphs. Union find with backtracking is another option, but it is less intuitive and involves added complexity in implementation. Tarjan's algorithm strikes a balance by offering optimal time complexity, O(n plus m), while requiring a manageable level of understanding for graph-theoretic concepts. Additionally, the problem of finding critical connections reduces neatly to the well-studied problem of identifying bridges. This reduction, coupled with the efficiency of Tarjan's algorithm, allows us to handle large-scale networks effectively without redundant computations. The problem at hand is to identify all critical connections in a network of servers, which can be modeled as a graph where servers are represented as nodes and their connections as edges. A critical connection, also known as a bridge, is an edge that, if removed, would increase the number of connected components in the graph, effectively disconnecting part of the network. To solve this, we can use Tarjan's algorithm, which is specifically designed to identify bridges in a graph efficiently. By performing a depth-first search, or DFS, we can compute two key properties for each node: its discovery time, which is the time at which the node is first visited, and its lowest point, which represents the smallest discovery time reachable from that node. The critical insight here is that an edge between nodes U and V is a bridge if the lowest point of V is greater than the discovery time of U. Using this, we can systematically identify all critical connections. To implement this approach, we'll rely on an adjacency list for representing the graph and maintain arrays for discovery times and lowest points, ensuring our solution is both time and space efficient. To implement the algorithm, we first use an adjacency list to represent the graph. This allows us to efficiently store all nodes and their neighbors, so that for any node I, graph I contains the list of nodes connected to it. Next, we initialize arrays for discovery times and lowest points, setting all values to -1 initially to indicate that nodes are unvisited. A visited array will also be used to track whether a node has already been processed during the DFS. Additionally, we maintain a list to store the bridges we identify. A global timer is used to assign discovery times incrementally as nodes are visited during the DFS. The traversal begins from an arbitrary starting node, typically node 0, and proceeds as follows. For each node U, we mark it as visited and set its discovery and lowest reachable times to the current value of the timer. The timer is then incremented before exploring all neighbors of node U. This ensures that the discovery time of each node is unique and helps us track the DFS progression. When exploring the neighbors of a node U during DFS, if a neighbor V has not been visited yet, we initiate a recursive DFS call on V. Once the DFS returns from V, we update the lowest point of U by taking the minimum of its current lowest point and the lowest point of V. This ensures that U's lowest point reflects all reachable nodes in its subtree. At this stage, we check whether the edge between U and V is a bridge by verifying if the lowest point of V is greater than the discovery time of U. If this condition is true, then removing the edge would disconnect the graph, confirming it as a critical connection. On the other hand, if V has already been visited and is not the parent of U in the DFS tree, we update the lowest point of U to the minimum of its current value and the discovery time of V. This accounts for back edges in the graph that allow you to reach earlier nodes without passing through its parent. Once all neighbors of U are processed, any identified bridges are added to the list of critical connections. When implementing this algorithm, it's important to consider edge cases to ensure robustness. For example, if the graph consists of a single node with no connections, the algorithm should return an empty list as there are no edges to evaluate. Similarly, in the case of a disconnected graph, the DFS must handle all components independently to ensure that every critical connection is identified across the entire graph. In scenarios where there are multiple critical connections, the algorithm systematically evaluates all edges, ensuring that none are missed. To see this in action, let's consider an example. Suppose we have 4 nodes and the connections are given as 0, 1, 1, 2, 2, 0, 1, 3. First, we represent the graph using an adjacency list. Node 0 is connected to nodes 1 and 2, node 1 is connected to nodes 0, 2, and 3, node 2 is connected to nodes 0 and 1, and node 3 is connected to node 1. With the graph constructed, we begin the DFS traversal starting from node 0. Starting from node 0, we set its discovery and lowest times to 0. From there, we visit its neighbor, node 1, setting its discovery and lowest times to 1. Continuing the traversal, we move to node 2, assigning it discovery and lowest times of 2. At this point, we backtrack to node 1 and update its lowest time to the minimum of its current lowest time and the lowest time of node 2, which results in a value of 0. Next, we explore another neighbor of node 1, which is node 3. Node 3 is assigned discovery and lowest times of 3. Here, we find that the edge, 1, 3, is critical, because the lowest time of node 3 is greater than the discovery time of node 1. This means removing this edge would disconnect the graph. Finally, the algorithm returns a list containing the critical connection, 1, 3. This demonstrates how the algorithm efficiently identifies and processes critical connections in the graph, ensuring accurate results through systematic DFS traversal. To solve the problem of finding critical connections in a network, we start by importing the default dict from the collections module to help us efficiently create an adjacency list representation of the graph. Inside the solution class, the method critical connections is defined, which takes the number of nodes n and a list of connections as input. The core of the solution revolves around a depth-first search, or DFS, which is implemented as a nested function within this method. The DFS function takes several parameters: the current node, its parent in the DFS tree, the discovery underscore time and low arrays to track the discovery times and the lowest reachable nodes, the graph representing the network, and the result list that will store the critical connections. Initially, the discovery and low values for the current node are set to the current time, which is then increment. Next, we iterate over all the neighbors of the current node. If a neighbor is the parent, we skip it since revisiting the parent is not useful. If the neighbor hasn't been visited yet, we recursively call the DFS on that neighbor. After returning from the recursive call, the low value of the current node is updated to reflect the lowest discovery time that can be reached from the subtree rooted at the neighbor. If the low value of the neighbor is greater than the discovery time of the current node, it means the connection between the current node and the neighbor is critical, so we add it to the result. On the other hand, if the neighbor has already been visited, we simply update the low value of the current node using the discovery time of the neighbor. Finally, the graph is constructed as an adjacency list where each node points to its directly connected neighbors. Next, we initialize the discovery underscore time and low arrays to -1 for all nodes, indicating that no nodes have been visited yet. The self.time variable is set to 0 to keep track of the discovery order, and an empty result list is created to store the critical connections. To ensure all nodes are processed, we iterate through each node from 0 to n1. For nodes that have not been visited, indicated by a discovery time of -1, we initiate a DFS starting from that node. The DFS explores all reachable nodes and updates the discovery underscore time and low arrays along the way, identifying critical connections in the process. Once the DFS completes for all nodes, the the result list will contain all edges that are critical for maintaining the connectivity of the network. Finally, we return the result, which gives us the desired output of critical connections in the network. Here, we begin by defining the Java implementation for finding critical connections in a network. First, we import the necessary utilities and set up our solution class. Inside the class, we initialize a variable time to keep track of the discovery time of each node during our depth-first search traversal. The main method, critical connections, takes in the number of nodes, n, and a list of connections representing edges in the graph. We create a result list to store the critical connections and use a hash map called graph to build the adjacency list representation of the network. We initialize the graph by adding an empty list for each node, and then we populate the adjacency list by iterating through the connections. For each edge, we add the neighboring nodes to each other's adjacency lists. Next, we define two arrays, discovery time and low, to store the discovery times and the lowest reachable times for each node. These arrays are initialized with -1 to indicate that the nodes haven't been visited yet. Finally, we prepare to perform a DFS traversal on each node if it hasn't already been visited, which we'll see shortly. If a node has not been visited, indicated by a discovery time of -1, we call the DFS helper function to explore that node. The DFS function takes several parameters: the current node, its parent, the discovery time and low arrays, the graph, and the result list. Inside the DFS, we first set the discovery and low times of the current node to the current value of time, and then increment time to ensure unique timestamps for subsequent nodes. Next, we iterate through the neighbors of the current node. If a neighbor is the parent node, we skip it to avoid revisiting the edge we just came from. If the neighbor hasn't been visited yet, indicated by a discovery time of -1, we recursively call DFS on the neighbor. After the recursive call, we update the low time of the current node as the minimum of its current low time and the low time of the neighbor. This step ensures that we capture the lowest point in the graph that can be reached from the current node. If the low time of the neighbor is greater than the discovery time of the current node, it means the edge between them is a critical connection. We then add this edge to the result list. If the neighbor has already been visited, meaning it has a valid discovery time, we update the low time of the current node to the minimum of its current low time and the discovery time of the neighbor. This ensures that we account for back edges that could connect the current node to earlier nodes in the DFS tree. With this logic, the DFS traversal effectively identifies and records all the critical connections in the network. Once the DFS completes for all nodes, the result list will contain the critical edges that, if removed, would disconnect parts of the network. This completes the implementation, and the function returns the result list containing these critical connections. To solve the problem of finding critical connections, let's start with example 1, where we have 4 nodes and the given connections. The first step is to construct the graph as an adjacency list, which allows us to efficiently represent and traverse the network. Here, the graph is built such that each node maps to a list of its directly connected neighbors. With the graph constructed, we then initialize 2 arrays, discovery_time and low, which will help us track the discovery time of each node during the depth-first search and the lowest discovery time reachable from each node, respectively. Initially, these arrays are filled with -1 to indicate that no nodes have been visited yet. Additionally, we initialize a variable self.time to 0 to keep track of the timestamp during the DFS, and an empty list called result to store the critical connections we find. This setup ensures that we are ready to begin our DFS traversal to identify the critical edges in the network. Starting the DFS, we begin with node 0. We set its discovery time and low link value to the current timestamp, which is 0, and then increment the timestamp. From node 0, we explore its neighbors, starting with node 1. Moving to node 1, we set its discovery and low values to 1, the current timestamp, and skip its parent node, which is 0, as it's already visited. We continue the DFS by exploring node 1's neighbor, node 2. At node 2, we assign it a discovery time and low value of 2. Here, we skip backtracking to node 1, its parent, and then begin backtracking, updating node 1's low link value to the minimum of its current low value and node 2's low value. This results in updating low 1 to 0. Similarly, when backtracking to node 0, we update its low link value to the minimum of its current low value and node 1's low value, which keeps low 0 at 0. At this point, we continue exploring node 0's other neighbor, node 3. At node 3, we set its discovery time and low value to the current timestamp, which is 3. Since node 3 has no unvisited neighbors apart from its parent, node 1, we backtrack and compare its low link value with node 1's discovery time. Since low, 3, is greater than discovery_time, 1, it means the edge, 1, 3, is a critical connection, and we add it to our result list. With the DFS traversal complete for this graph, the final result contains only one critical connection, 1, 3. This concludes example 1. Now, let's consider a new example 2, where the graph is disconnected. Here, we have 6 nodes and 2 separate components. After constructing the graph as an adjacency list, we see that nodes 0, 1, and 2 form one component, while nodes 3, 4, and 5 form another. In the first component, consisting of nodes 0, 1, and 2, we perform a DFS traversal similar to example 1. Since this subgraph forms a cycle, there are no critical connections in this component, as removing any single edge won't disconnect the graph. Moving to the second component, which consists of nodes 3, 4, and 5, we start the DFS at node 3 and traverse to node 4, then to node 5. During backtracking, we find that the edges 4, 5, and 3, 4 are critical connections, as removing either of these edges would disconnect the graph. After completing the traversal of both components, the final result for this example is 4, 5, 3, 4. Now, let's examine example 3, which illustrates a star topology. In this example, we have 5 nodes arranged in a star topology, with node 0 at the center connected to all other nodes. Constructing the graph as an adjacency list, we see that node 0 has neighbors 1, 2, 3, and 4, while each of these neighbors connects back only to node 0. During the DFS, starting at node 0, we traverse each of its neighbors one by one. Since all these neighbors are leaves with no other connections, each edge from node 0 to its neighbors becomes a critical connection. Removing any one of these edges would disconnect the corresponding leaf node from the graph. As a result, the final list of critical connections in this example is 0, 1, 0, 2, 0, 3, 0, 4. This demonstrates how a star topology can have all its edges classified as critical connections. The time complexity of this solution is O, V plus E, where V represents the number of nodes or vertices in the graph, and E represents the number of edges. Let's break this down step by step. First, we have the graph construction phase. Here, we build the adjacency list from the given connections input. This requires iterating through all the edges in the graph, which takes O, E, time. Next, we perform a depth-first search, or DFS, to explore the graph. During this traversal, we visit each node once and iterate through all edges connected to those nodes. Since the total number of edges is E, the DFS traversal takes O, V plus E, time. When we combine the time taken by the graph construction and the DFS traversal, we get an overall time complexity of O, V plus E. This linear complexity ensures that the algorithm is efficient, even when the graph is large. Now, let's look at the space complexity of the solution, which is also O, V plus E. First, consider the adjacency list used to represent the graph. This list requires O, V plus E, space because we store each node as a key and maintain a list of its neighbors, which corresponds to all the edges. Additionally, we use auxiliary arrays like discovery_time and low to store integer values for each node. Since there are V nodes, these arrays require O, V, space. Finally, we must account for the recursion stack used during the DFS traversal. In the worst-case scenario, where the graph is structured as a single path, the recursion stack depth can reach O, V. Adding these contributions together, the overall space complexity becomes O, V plus E. Whether the graph is minimally connected like a tree or densely connected, the algorithm processes all nodes and edges, so the time complexity remains O, V plus E, in all cases. Let's compare this optimized approach to a brute force method. A naive solution would involve removing each edge one at a time, checking if the graph stays connected, and identifying critical edges. This requires performing a connectivity check, such as a DFS or BFS, for each edge. Since each connectivity check takes O, V plus E, time and there are E edges, the total time complexity of the brute force approach is O, E asterisk, V plus E. In contrast, the optimized solution leverages Tarjan's algorithm to calculate discovery and load times for each node in a single DFS traversal. This reduces the time complexity to O(V plus E). To confirm this mathematically, note that each edge is traversed exactly once during the DFS, contributing O(E). Each node is also visited exactly once, contributing O(V). Adding the graph construction cost of O(E), the total time complexity is O(V plus E), making it linear with respect to the size of the graph. This efficiency highlights the power of the optimized approach. In this section, we'll discuss some common mistakes that often occur when solving the critical connections in a network problem. First, not accounting for bidirectional edges is a frequent issue. Since the graph is undirected, edges must be added in both directions when building the adjacency list. If this step is missed, the graph representation becomes incomplete, and algorithms like DFS or Tarjan's algorithm may fail to traverse all nodes properly. Next, incorrect initialization of discovery times can lead to errors in identifying bridges. This happens when discovery times are not updated during DFS traversal or are initialized incorrectly. A good practice is to use a default value, such as -1, to represent unvisited nodes. Another critical error is misunderstanding or mishandling low-link values. The low array is essential for determining whether a node is part of a cycle, and any mistake in updating it can cause failures in identifying critical edges. Lastly, revisiting already visited nodes without proper checks can result in infinite loops or redundant computations. To prevent this, use a parent parameter during DFS to ensure the immediate parent isn't revisited unnecessarily. Now, let's focus on some performance-related issues and interview insights. For large graphs, using inefficient algorithms with high time complexity, like O(n²), can lead to time limit exceeded errors. To handle such cases efficiently, Tarjan's algorithm is the recommended approach, as it runs in O(V plus E) time. From an interview perspective, this problem highlights the classic use case of finding bridges in a graph. Interviewers often evaluate your understanding of low-link values and their role in identifying critical edges. If you can't implement Tarjan's algorithm, you should discuss alternative approaches, such as brute force methods that remove edges one by one and test connectivity. However, be sure to emphasize the inefficiency of this approach. Additionally, don't overlook edge cases like disconnected graphs, single-node graphs, or graphs with no critical connections. Lastly, make sure you can clearly explain the recursive DFS process and how discovery and low-link values are tracked during traversal. Next, let's explore related problems and alternative approaches. Some problems you might encounter that involve similar graph traversal techniques include LeetCode 323, which focuses on counting the number of connected components in an undirected graph, and LeetCode 310, which deals with finding minimum height trees, a problem requiring a good understanding of tree properties. Other relevant problems include LeetCode 785, which asks if a graph is bipartite, and LeetCode 743, which focuses on network delay time and involves shortest path algorithms like Dijkstra's or Bellman-Ford. When it comes to solving the critical connections problem, there are a few approaches worth discussing. A brute force method involves removing each edge one at a time and checking graph connectivity using BFS or DFS. While simple, this method is highly inefficient with a time complexity of O(E*)(V plus E), making it unsuitable for large graphs. Tarjan's algorithm, on the other hand, provides an optimal solution with O(V plus E) complexity. While it requires a solid understanding of graph theory and low-link values, it is by far the most efficient approach. Alternatively, you could use a union-find approach to detect bridges, though it's less intuitive for this specific problem compared to Tarjan's algorithm. Finally, let's wrap up with some key tips to keep in mind. Always test your solution on a variety of edge cases. These include single-node graphs, fully connected graphs, and graphs with no critical edges. Understanding these cases ensures your solution is robust. During interviews, it's important to clearly explain the role of discovery and low-link values in Tarjan's algorithm, as this demonstrates your grasp of the underlying concepts. When implementing your solution, use adjacency lists for representing the graph. This is particularly efficient for sparse graphs, where the number of edges is much smaller than the number of nodes. By following these tips, you'll be better prepared to tackle both this problem and similar graph-related challenges in interviews. Great job! To wrap up, we discussed the DFS-based approach to solving critical connections in a network. You learned about the concept of bridges in graph theory and how DFS can be applied efficiently to identify them. Keep practicing these techniques to strengthen your problem-solving skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!